So one last example of being able to work with these second-order differential equations, solving them by Laplace transforms. This time we have a non-homogeneous differential. So we have our y double prime minus y prime equals e to the t cos t. Y at 0 is 0, y prime at 0 is also 0. Note that if you were trying to use a method such as undetermined coefficients or even our variation of parameters method, this might be fairly rigorous to go through and do that. So let's see if there's any benefit to using Laplace transforms. So we have our Laplace of y double prime minus Laplace of y prime, and that's going to be equal to the Laplace of e to the t cos t. And we already know how to take the Laplace of the second derivative, so that's going to be s squared Laplace of y minus sy at 0 minus y prime at 0 minus the quantity of s Laplace of y minus y at 0, and that's going to be equal to the Laplace of e to the t cos t. Now we can think of this as s approaches s minus 1, since this is e to the t, where a is going to be equal to 1, and we can use that first translation theorem. We know that cosine of t is s over s squared plus 1 for cosine, so all we're going to do is we're just going to plug in s minus 1, and so we're going to get s minus 1 divided by s minus 1 squared plus 1. And the good news is that anything that has a y at 0 or a y prime at 0, because of the initial conditions, those are going to cancel. And so what we end up with now is we have our s squared Laplace of y minus s Laplace of y is going to be equal to s minus 1 squared plus 1. Right? And then finally what we can do is we can go through, factor out an ly, so Laplace of y, and we will be left with s squared minus s equals s minus 1 over s minus 1 squared plus 1. Now this can get really ugly really quickly if we don't do some algebraic simplification when we solve for Ly. So the Laplace of y is going to be equal to, now be careful with this, s minus 1 in the numerator, s minus 1 squared minus 1 times s squared minus s. Right? So notice I didn't FOIL anything out, and generally foiling is going to make things pretty difficult. So an alternative method to being able to write s squared minus s is we could just factor in s out. So let's just go ahead and rewrite this as s minus 1 times s, and notice that we got lucky in this one, as if somebody actually made it so this problem will work out like that, and we get rid of those, and so now we're left with Ly of 1 over s minus 1 squared minus 1 times s. Right? And so that's not too bad. Now what we'd like to be able to do is perhaps do a decomposition of this, all right? Because notice we have an s right here, and then we have another factor. So I think what we should probably do is FOIL out this s minus 1 squared minus 1, and then combine like terms. So after just a little bit of algebra foiling this out, we're going to end up with 1 over, I'm going to just move the s in front as a coefficient. We get s squared minus 2s, and then we have this minus 1. Oh, and by the way, this should be a plus 1. I think I made a copy error right here. So this should be a plus, this should be a plus. And so we're going to get a plus 1, so we're going to go plus 2. All right. Now we're going to go through. We're going to take the inverse Laplace of both sides. So Laplace minus 1 of Laplace y is going to be equal to inverse Laplace of 1 over s squared minus 2s plus 2. And clearly the left-hand side is going to become y. And then the right-hand side is the one we're going to have to work on. So L minus 1 of 1 over s squared minus 2s plus 2. Right. And at this point now we can go ahead and try to do our decomposition. All right. So notice that we have one linear term in the denominator, and then we also have one quadratic term. So we're going to have two different sort of factors, fractions that we're going to look at. So let's just go ahead and do the decomposition. So 1 over s squared minus 2s plus 2 is going to be equal to a over s plus bs plus c over s squared minus 2s plus 2. And then, just like we've done before, we're going to multiply through by the common denominator of s squared minus 2s plus 2. So we get 1 is equal to a. Now the s is going to cancel with the s in the denominator here. So we're just going to be left with the s squared minus 2s plus 2. And then we have that bs plus c times s. Just like we've done before, we're going to FOIL out. So 1 equals as squared minus 2as plus 2a plus bs squared plus cs. And then we can finally go ahead, factor out the s squared, factor out the s, and collect what's like. And so we also are going to write the left-hand side as 0s squared plus 0s plus 1, just so that we have a placeholder, factoring out the s squared from a and b. And then also factoring out the s from negative 2as, and cs is going to leave us with a negative 2a plus c. And then we have that 2a that's kind of hanging out. And what does our system become? Pretty easy, actually. All right, so if we get to our system, we're going to wind up with a plus b is equal to 0. We're going to end up with minus 2a plus c is equal to 0. And then we're also going to end up with 2a equals 1. And that makes this a really easy system because now we already have what a is a half. Just seems like we keep getting a halves for all of these. We know that a plus b is equal to 0, so that means that b is equal to the opposite of a, or b is minus 1/2. And then finally, negative 2a plus c is going to be equal to 0, so minus 2 times a half plus c equals 0. Clearly that's going to be 1 just by going through and solving. Okay, so now we have all the different coefficients for us, and we can go ahead and substitute those back in to our original decomposition and then find the inverse Laplace of that. All right, so now we're going to have that y is going to be equal to inverse Laplace. We know that a is a half over s, so that's the easy one. Not so easy is this animal. It's going to have minus 1/2 s plus 1. And then we remember in the denominator we had s squared minus 2s plus 2. All right. And how do we go from here? Well, remember that trick that we've used before where we go through and we just split things up? All right, so we're going to split up this last term. This is probably going to be a really easy one. We can factor out the half. So we're going to have 1/2 inverse Laplace of 1 over s, which is just going to become a half at some point, plus, I'm going to factor out the minus 1/2 from the minus 1/2 s. Make this a little bit easier. So we're going to have minus 1/2 inverse Laplace of s over s squared minus 2s plus 2, and then finally plus a single Laplace of 1 over s squared minus 2s plus 2. Alright, now, these guys are a little bit tricky. Alright, so we're going to have y equals, we still have that 1/2 inverse Laplace of 1 over s minus 1/2 inverse Laplace. We could try to complete the square as we did before, and I think that's probably going to be the way we should remember how to do that. Remember earlier that we had that this was s minus 1 square plus 1, and I'm going to go through and do that just to make sure we all understand how to get that. But we could rewrite that as s squared minus 2s plus 1 instead of that plus 2, which is the same thing as s minus 1 squared plus 1. Earlier when we did this problem, earlier in this problem, we FOILed that out. All right, so now we're just factoring it back. All right, so that's going to be inverse Laplace of our s over s minus 1 squared plus 1. And then same thing here, plus inverse Laplace of the 1 over s squared minus 2s plus 2. All right. And we did say that we were going to factor that. So let me erase this, write it into the factored form. Otherwise, we're not really getting too much further with it. S minus 1 squared plus 1. All right, so what do we do at this point? Well, the good news is that this one's ready to go, and this one's ready to go. All right, this one's just the first, this third one, this third term is just a translation theorem. That's nice and easy. This one's just a 1, which is easy. Unfortunately, this one's not ready to go, all right, because we have an s minus 1 and then an s. These both have to be the same thing. So what are we going to do? We're going to do that magic trick where we are going to subtract 1 and add 1. Right? And what that's going to do is that's actually going to split off another Laplace transform because of this 1. Okay, so let's rewrite this at least one last time. So y is going to be equal to 1/2 inverse Laplace of 1 over s minus 1/2 inverse Laplace of s minus 1 over s minus 1 squared plus 1. Now we have this 1, all right, but we also have a negative 1/2. So we have negative 1/2 times 1, which is just going to be another negative 1/2. So that's going to be minus 1/2 inverse Laplace of 1 over s minus 1 squared plus 1. But then we also have this animal, which is going to be plus 1 over s minus 1 squared plus 1. Now I want you to notice that this term and this term are like. So we actually have a negative 1/2 and we have a positive 1. So that's just going to turn into a half. And right before we do this, we can also do the translation theorem. So we're going to combine these, and we're going to get a half out of those two. So y, before we go through and do the actual transform, y is going to be equal to 1/2 inverse Laplace of 1 over s. We're going to use the first translation theorem, minus 1/2 Laplace inverse of s over s squared plus 1 as s approaches s minus 1. And then remember we have a plus 1/2 from right here because we combine those of 1 over s squared plus 1 as s approaches s minus 1. Right, so we have our three terms, and finally we can go through and get an answer. Right? That's just 1, so we get 1/2 times 1. Remember, this is going to be cos of t, but then we have this s minus 1, so that's going to be an e to the t, where a is 1 from our first translation theorem. So we're going to have minus 1/2 cos t e to the t. And then finally, we're going to have plus 1/2. This is going to be our sine of t. And then we have an e to the at, where a is equal to 1. So that's going to be plus 1/2 sine t e to the t. All right. We could certainly factor out a half, make this a little bit more clean. So one final way of writing this, if we really wanted to, was 1 minus 1/2 e to the t cos t, not 1/2, we just factored that out, sorry, plus e to the t sine t. Alright, so, not sure if that was easier trying to use a Laplace transform to be able to get to the solution as opposed to undetermined coefficients or a variation of parameters, but it is a way to be able to solve it, okay, while minimizing our calculation errors, all right, but we do have a lot more algebra intensive steps going on here. All right, so hopefully this gives you 4 good examples overall of being able to work with the Laplace transforms and also going through the different methods of doing the inverse Laplace, which as we know is the trickiest part.